morning, buddy. How you doing?
Uh-oh. My camera isn't showing up.
Oh, no. Yeah,
The light is on.
No, I see the problem. I made some changes, and we didn't test this one right here. But while you are saying this, I'm going to do that.
Okay.
And then I'm going to do that. There we go. That's actual size, kids. Right there. That's how big I am. That's how tiny he is. Thoughts?
Okay.
Any thoughts on that, Campbell?
I like it. It's fine.
Yeah? All right, cool. Let me just flip you over here on this one, too, while I'm on the screen there. There you go. Now you flip. Give me a high five, man. Ready to write some code?
My hand doesn't reach there.
All right, fine. I'll make you bigger. Do you want to write some code, man?
Yeah.
Are you up for that? What's the real actual size? It's about like there. That's kind of what it is.
I think it's a bit smaller.
Maybe a little bit smaller. Right about there. That's what camera is really in relative to me. Let's bring that back down there so you're behind the little electrical field. Yeah. Let's start with a little thing we could say, Nicole.
What happened last time?
That's what we're going to do. And we'll switch over to Campbell's machine.
Well, last time, if we go back to the code, we worked on the solver 4x4, I believe, right? Was that last show?
4x4.
And the solver 5x5.
We added a 5x5. So basically, we started a couple weeks ago with a 3x3 rule, an observation that if we had three numbers in three squares, and that was the only thing in those three squares, then they had to be in some combination, which means they could not be any other squares.
And then we did the same thing with the solver 2x2, which is a very similar rule, just with two squares, with two things.
Yes, as I recall, it's different. There's the code on the solver 4x4, 3x3, and 5x5 is very similar. But the 2x2 was really different, as I recall. We wrote this one first. Basically, if I have two numbers in one, and a square and the same two numbers in another, and that's all I have in those two squares, those numbers can't be anywhere else.
In that row or column or block.
Yeah. The thing that's interesting is that the solver 3x3, the solver 4x4, and the solver 5x5, they all descend from solver n by n. Right? In fact, there's a key that you can choose in CodeRush here called go to derive types of solver n by n, and there you can see all three of them right there. So all three of those derive from solver n by n. And they all essentially have logic that kind of looks something like this, where we're going to go through, and all this logic is doing, Campbell, I'm not sure if you remember this or not.
It's going through the for loops, and then each time we add a for loop, right? For each
Well, it's definitely going through the for loops, but the whole purpose of this is to find, in the 3x3, is to find three squares that are unique. That are not the same. In other words, I can't have the first square, and the first square as those three squares. I need first, second, and third. Or I need first, third, and fourth. Or I need second, third, and fourth. All this code is doing here, this outer loop is iterating through all of the squares in the group. This inner loop is then doing the same thing, but checking to see if the second is equal to the first. And if it is, it does continue. We can't have, two of those or three of those being the same square.
Yeah.
Then the third one does the same thing. It goes through all of them. Because they're nested, we're going to go through all the combinations.
And this one, it checks to see if the third is equal to the first or the third is equal to the second. But then, if either of those are true, then we
exactly.
go through.
And then at this point, I like to write the word magic when something cool happens in the code. And we can say, like magic, we have three unique indices.
Well, those three were always unique, but we found them.
Well, yeah, because of this code and because of this code, they're guaranteed to be unique by the time we get into this block. If the code is here, we have three unique indices. Once we have three, we can add those to our list of indices and it's called solve for many, which is in the ancestor class. That solve for many, you can see, is called by the solver 5x5, the solver 4x4, and all that's doing is just extending that logic out to get five unique ones or four unique ones, that sort of thing. Yeah. Solve for many is implemented up here, and that's what it does in the solver n by n. Goes through and does that. I think I added a parameter anticipation of a new rule. Yeah, the group kind parameter is not being used right now, but group kind tells us what kind of group we have. is it a row, is it a column, or is it a block? And the reason why is, I think about a week and a half ago, Campbell, you remember we were talking about this other rule that we could potentially add, where information in a row or a column could have leakage implications into the block that the column passed through, into the blocks that the column passed through, or the row passed through,
Yeah.
that sort of thing. We were talking about that. I'll go over that today if we have time to implement that. But that rule, in order to implement that rule, we're going to need to know what kind of group we are. Are we in a row, or are we in a column, or are we in a block? Okay?
And sorry, another feature we added was the Control Z.
Undo and redo.
Yes.
We had problems at the end of the last
just
show.
undo. We were only able to. Well, we tried to add both undo and redo, and we didn't quite finish undo, and we figured out why. And so this is undo working, and so the reason undo wasn't working is because we had we weren't sorry, the app, this app was also has an undo statement, I guess, or a thing that says control the when you
An
hit
ability to
Control Z.
hear that or to listen for that.
Yes, and
That
then
Control
undo.
Z.
And
Yeah,
so
it's not the app. It's actually every text box that we're using to put those numbers in. Every text box has Control Z built in if it has focus. So what was happening is we were intercepting the Control Z. We were undoing it.
and then it was undoing our undo.
And then the text box saw the Control Z and was saying, well, I'm going to undo it again. So we were seeing no changes. And when we traced it, we were seeing this mysterious call back to text change. The change was happening, but from nowhere in our code were we seeing that. And we stopped the show, and whenever I'm like stuck on a problem, I cannot stop looking at it. And so I kept looking at it for like, I think about another 20 minutes before all of a sudden it occurred to me, I wonder if the text box might be interfering.
I
Is
think
it possible?
what we might want to do if we undo, we should update the notes in that text box that we undo from. Because now if I try to hit solve, nothing will happen.
Ah, because the
Oh, wait.
the
Never
notes are
mind.
wrong. Oh no.
Oh, because it gives it notes when you hit solve, right?
What'd you say?
Never mind.
Oh, solve maybe updates the notes automatically,
does.
but maybe you're right. We should update those notes as we go backwards. I like that. I'll tell you something else that kind of bugs me about this. If you move the arrow keys, go ahead and move the arrow keys, Camel. Hit those. See what's happening? That's our focus piece. But now click on like the 5 in the center of the board.
Oh yeah, it doesn't
Yellow
bring
doesn't
selection.
That kind of bugs me.
If you have your caret here and then you use the arrow keys, it goes
It
back.
goes back to that? Yeah,
Yeah.
that's problematic. So I want to fix that. There's some little things we want to fix. We want to add redo. We want to, the other thing I wanted to do is when we undo, it would be nice to highlight, to move that selector to the piece that just got undone.
Oh, maybe.
Right? So we can actually visually see where the undo pieces are going from. Right? The whole point of good design, Campbell, is making it so that the brain of the person using your software and the body of the person that's using your software has to work less, doesn't have to work so hard. So we want to make it so that there's less effort. Wow, that solved quickly.
It's 3 clicks.
3 clicks?
Remember? For the easy game.
The easy game. That means our rules are getting really, really good. I think what's interesting is what happens if we add our new one. What we should do is get some benchmarks before we start. Load up each of the games and write down somewhere how many solves it takes to solve them.
All right.
Okay? And I think there's still one that we can't solve. I think, as I recall.
There is. It's a Control Alt docs.
There's one that we can't solve without a brute force attack. But I'm interested to know that if we implement this other rule, if by chance that other rule will open it up and break it open for us.
Sudoku benchmarks.
Are you writing down some benchmarks?
Mm-hmm.
Okay, cool.
Yeah.
Nice. Okay. Sudoku
Okay.
benchmarks. So we have 4 different games that we have kind of preloaded. We have the easy game.
Easy. game.
This actually might. I wonder if it makes sense. Yeah, go ahead. No, go ahead. Do what you're doing.
3 clicks. Or
Okay.
3 solves, I guess. Yeah.
3. Okay. You just hit the number 3 there too if you want. I will know what this means in about 30 minutes from now, 40 minutes from now,
Oh, that's true. But
2 hours from now. All right. You can
And then
copy
we
each
do
one
the-
too. Copy each line, so you only have to type in the word medium or whatever.
oh,
Copy just the word game all the way to the end. There you go.
Control C.
Medium game. Paste.
Oh.
And how many solves is the medium game?
Let's see. I think we might have to use the brute force on the medium game. It's wait, control. Yeah. 3, 4, 5,
Excuse me.
6, 7, 8, 9, 9 solves.
It wasn't 10? Or you were saying the number just before you clicked it?
Yes.
Okay. The medium game is 9 to solve it.
Oops.
Cool. Yeah, this is actually like one of the things, it's kind of taking careful notes that I find leads to higher quality code.
I think, oh wait, no, it's this one that we have to use the brute force on. We'll use Control Shift, load game.
So Camel's holding down the control key, the shift key, and hitting load game.
Yeah.
And then
1,
that's loading up the game that we have
2,
stored in the code.
3, 4, 5, 6, 7, 7. 'Cause the
7,
la-
we get to a block.
Yes,
So let's write
and
that
then-
down.
Okay.
At 7, we get to a block.
Oops.
Because it could be that maybe with the new rule, we go to 5 and we get a block. And do you know what I mean? It's like,
Yeah.
and then say 7
2,
solves block. Something like that. You don't solve it.
Yeah, I think I'm just going to do 7 solves and then that arrow and then 1 brute force. I think it's 1 brute force.
Yeah.
Wait,
yeah.
let me check.
Yeah, brute force only is. Oh, but you could do hint, actually. You should do is get to the 7, hit hint, and then how many more?
Ah,
Right?
okay.
Because I think that's like a little more indicative. Because the brute force always will solve it.
That's true.
So say 7 solves a hint.
Okay, control. Yep, okay, so 7 hint.
And now try solve.
So 1 hint. 1, 2, 3.
Okay? Good. 1 hint, 3 solves. So that's not bad.
1.
1 hint means we do brute force, we go forward and see what goes in that square.
And then 3
3
clicks.
solves.
Yeah, 3 solves. 3 solves.
Alright? Cool.
And then this one is the expert game we're calling it.
Yeah, expert game. Which I think is not as hard as the hard game for our program to solve.
Really?
Yeah, I think that with the expert game we solve, right?
I don't think so.
Oh, okay. Expert game
Yeah,
is
Control Alt Shift.
Shift, and load game.
Okay. 1, 2, 2, and then we hit a block.
Oh, okay. I'm bad. My bad on that. Okay, 2 solves, 1 just do a hint.
2 solves. 2.
Just copy the whole 1 hint above you if you want. It's like right. Yeah, there you go. And now how many solves now?
Let's see. 1 hint. This might take a while. Oh, that's a lot of combinations.
Yeah, it is a lot of combinations. You can see them up at the top there. It's a big number in the title bar there. That might take a while. Okay. While that's running, we can switch over to my machine, and I'll talk about the logic rule I want to create.
Okay. I'll tell you when it updates.
Perfect. All right, let me open up the Sudoku PowerPoint. Where is it? No pen at all anywhere on the screen. Let's run my pen driver here. Any more luck? No, where's the tablet driver? We're gonna have to go and fix it in the tablet driver. Work area. What's going on? You're gonna really make me upgrade? It's just, if it doesn't see it, I'm gonna unplug it, the tablet for a second, replug it in. How's that? Any better? Got a work area. Okay, good. It looks like now we're gonna be working. Okay, cool. Good. All right. So let's look at this. This is, as I recall, a little tricky to conceptualize.
Yeah.
But the idea is this idea of maybe, I don't know if I should write a text or not. I think I'm going to just, we'll do this for now. So this idea of kind of, what'd you say?
Can I say something really quickly?
Yep.
Yeah, so I think that we should add in our brute force thing, every time it like checks to see if a possibility works, it should also try to do the 2x2 rule, the 3x3 rule, even our 1x1 rule.
Right, we were talking about that. Yeah, no, I agree with that. The brute force runs, then it does a whole bunch of its things. I think that's going to reduce the time for the brute force attack.
Yeah.
Every time it makes a guess, it runs for everything, so it can much more quickly find error problems than not. Okay, so I want to talk about leakage here. This idea of it's kind of like information or conclusion leakage is kind of the idea. We can be conclusion leakage is what I'm going to call this. I don't have a better name for it, but the idea is that I'm looking at a row or a column of Sudoku squares. I can infer things about the block that some of these are contained in. Like this, I can infer things about this block based on what's in here. Okay? That may be like, looks like I got way too many squares here or there, but you just imagine that this is correct, right? There's nothing there, really, and there's nothing over here, right? Like that. So I can infer things about this block. That is basically what we discovered. And so the idea, if you look at one of these rules, like let's start off with maybe the 3x3 rule.
Dad.
Yeah.
I think I found a bug in our code.
Oh, really? You want to switch to your machine?
Yes. So I found. Oh wait. Oh, sorry. Never mind.
We'll switch back to my machine.
Sorry.
Nothing?
I thought I had found an instance of the solver 4x4, but really it was just like a solver 4x3, I guess.
Maybe. Can you show me actually?
Yeah.
You saw one that it should have used and it didn't?
I thought that it should have used.
Show me.
So look, 2579, 2579, 257.
Yeah.
And it was like, sevens and fives and sevens and fives should
You need one more
fives.
square. Got it.
Yeah.
You definitely need one more square. Okay, cool. All right. So here's an example, right? If we look at the 3x3 rule, the 3x3 rule, it looks for 3 squares that collectively, among those 3, contain only 3 numbers. Right? What that means is those numbers are only in those 3 squares and nowhere else. Right? That's what we're talking about. They can't be anywhere else because if the note is there, that means it's a possibility of being there. And if the note's not there, it can't be there. So the only numbers that can be there are those 3 numbers. So only 3 numbers, right? Oops, only 3 numbers like that. So that's the 3x3 rule, the essence of that. If we find that, if we satisfy that in this row, the next question is, where are those relative to the blocks? What blocks are those under? So this is the next step, the next level up. What blocks are those 3 in? And if they are in 2 or more different blocks, are those numbers in? Right? And the implication here, let's get to a new page here. If there are 2 or more blocks, then that's where we have this kind of conclusion leakage, where we can make a conclusion about the group that we otherwise have no information about with those three numbers, or the 4 or the 5, because this logic should work for the 3 by 3, should work for the 4 by 4, should work for the 5 by 5. So as a specific example, let's bring this up again here. Yes. 1, 2, 3, 4, 5, 6, 7, 8, 9. And we have a block, let's say we'll have a block right here. So let's say, and if we look at this, if we look at the whole big picture of everything, we look at all of the blocks on the board. The blocks are the groups of 9 by 9 groups right here. What I want to do is I want to label these like B1, this is B2, this is B3, right? B4, B5, B6, B7, B8, and B9. Those are the different blocks. So let's say this is up here at B2, right? That's B2 right up there, okay? Well, that means this block right here is B1, right? So that means I'm getting B1 here, okay? So that's B1, that's B2, and over here is B3, right? In fact, what I should have done is I should have taken this and put it inside like that, and then this one's B3. All right, you with me so far, Campbell?
Yeah.
All right. So let's say that out of this we have, let's just give a real example. We'll keep it simple with the 3 by 3. So let's say over here we have 1 and a 2 in the notes. Okay? And over here we have a 2 and a 3 in the notes. And over here we have a 1 and a 3 in the notes. Something along those lines. Okay? So what that means is that we now have, in the B2 block, right? We have 1, 2, and 3. That's in B2, right? If we just collect and we look at all the ones that are matching in our 3 by 3, if we check to see what groups we're in and we just start listing them out, well, we've got a B2 that's got all of those numbers in it. And all of those in that group that are in the B1 look like this. B1 has got a 1 and a 2, okay? And then what we do is this, is we subtract. We basically subtract, or we remove elements from the set. So we do this. We say, what is essentially B2 minus B1? B2 minus B1. And we also want to ask the question, what will B1 minus B2? All right, if we say B2 minus B1, that's equal to 3. All right, and what that means is that the 3 has to be somewhere in these 3, which means there cannot be a 3 anywhere in B2. So what that means this implies, okay, there's no 3 in other squares of B2. That makes sense in 1, 2, 3, 4, 5, 6, other 6 squares. You with me on that, Campbell, or no?
Yes.
Other B2 squares. Okay? B1 minus B2 is the empty set. We're essentially getting nothing there. Sometimes we draw it like that, I think, which means nothing we can do. There's no information we have. Okay? But if we switched it around and we said, well, in B1 there's 1, 2, and 3, right? And in B2, let's go that, which is 1 and 2, right? Then the whole thing changes up, right? In other words, you get this one goes down here and this one goes up here, whoops, right here, and it's the starting piece. This is becomes B1 right here. If that makes sense. Oops. And I'm just realizing instead of doing all that undo, I should have just made it around a new picture for you, kind of a thing like that. But the logic works either way. Right? You're just basically saying, okay, I'm taking one and subtracting the other. Now, I think it's also possible. Is it possible? It might be possible to get empty sets for both subtractions in which there's nothing that can be inferred. And what I mean by empty sets in both subtractions, what I mean is that this would have, like, for example, a 1 and a 3 in it. And the other one would have a 1 and a 2. And then
Okay.
in that case, we have nothing left over. It's an empty case, an empty set in both.
All right. Okay.
You got all right because what?
Huh?
All right just because you get it, or all right because you got results on the hint?
Oh no, because I got it. I understand. I have not gotten a result on the hint yet.
Did you get that error in Visual Studio or
Yeah.
that warning?
This is in break mode.
Yeah.
I did.
Yeah, okay, cool. All right. So that's the logic. That's kind of what we're looking for. I guess, while we're waiting for yours to go through is trillions and trillions and trillions and trillions of combinations. We'll implement this, I think. Do you want to do that or on my machine, or do you want to do redo?
Oh,
Or do you
I
want
just got the result.
Oh, cool. Switching over to Campbell's machine.
Okay. So then we have one hint, and
Yeah.
then we have one solve, two solves, three,
No, we're stuck at 2 solves.
three. Yeah, two solves, and that's it.
Okay. All right, so let's do it. So we have to, one hint, 2 solves, then one hint again. Although this hint should be much faster.
Yes.
I'd say theoretically it should be much faster. We also might want to put in that one hint took like about 10 minutes.
Yeah.
We might want to include that in the data over there so that if we do try this technique you're suggesting of running our logic between every guess,
Okay.
I estimate it was about 10 minutes. Just put 10 minutes in there, just save space.
Okay. To one hint.
Okay? Did you hit the hint button yet or no?
No. I will now though.
Noting the time is about 10:42. Okay, we'll let that go. Or what do you want to do? Do you want to work on the thing where we get the highlighting to follow, where we click? Do we start off easy?
Let's work on redo, because I think that will be fairly simple now that we have undo.
The redo? Okay, let's work on redo. Don't stop on your machine because you're still running. We'll do it on my machine. Is that cool?
Okay.
Okay. So switch it over to my machine. Bring up the Sudoku app. Main window is where I think we have undo. There it is right there. If Z is equal to Z, T is equal to Z, and modifier has flag, modifier key is control, then we're going to go to do command invoker.undo. And this is the piece that fixed the bug. E.handle is equal to true.
Yeah.
It's a WPF thing. WPF is the framework, Campbell, that lets us
That
build
we're
this application.
working, yes.
So it looks like, all right. What's my undo key, Campbell? Do you like Control Y or Control Shift Z? Do you have a preference?
Well, would it be hard to do both?
No.
Okay.
So we're just going to
Let's
say
do both.
if key is equal to this, and it has flag Control, and it has flag Shift. And it's Control Shift Z, like that's one.
And
then
then
I'm also
Y.
like, or, what'd you say?
Yeah. Nothing.
Down here I'm going to say key is equal to Y,
And then we
and
just want
Control only. Now, by the way, you know about operator precedence, like if I have, 4 plus, if I have, an equation that looks like this, something like 4 plus 5 times 3, 3.
Yes,
that I do this first.
yes.
In Boolean logic, there's an operator, in computer science, there's an operator order preference which says do the ampersand, the double ampersand, or the and logic operation before you do the or.
Oh.
So what happens is it's going to do all of this first, or it's going to do all of that. Now, if you're ever not sure, Campbell, if you just want to be really extra safe, you can put parens around each piece, right? You can use parens just like you can, whoops, not there, right there, right? So you can use parens like this and like this. See that? See what I'm
Oh
doing?
yeah, because otherwise, like if it didn't have that order of operations thing here, it might think that if it has shift and it has Y down as well, then it would.
Yeah. You might get to this point here, like we leave it like this, where if we didn't have that, or if it was an opposite preference where the or was operated on first, you would say, well, if it's shift or, the keys down, or you just hit the letter Y, right?
Yeah.
So that's what's going on there. The other thing you can do, if you're not, you want to be really super clear, is you just take this out and you introduce a new local for it, right there, and you're going to call this Control Shift Z press. Like that.
Yeah.
And similarly, you're going to come in here and you're going to introduce a local for that. And you're going to call that Control Y press. And now, all of a sudden, you see kind of the true logic,
Yeah.
right? Does that make sense? So now what we're going to do is call redo instead, which we don't have. But that's okay. We'll figure it out. We'll add it in here. Here's our undo. So we have this thing called an undo stack. Right? And you know what a stack is? Do you remember that, Campbell?
Yes. It's when if you put something on it, it will take off the last one.
Right, exactly. Like here I have I'm incredibly fortunate to have a canister of both cashews and another canister of macadamia nuts. And I can stack them like this. But the way a stack works is if I want to get something from the stack, I have to take it from the top.
Yes.
That's what happens. And then this one kind of bubbles up from the top, and okay, I'll take that one. And oh, look, there's another one right underneath that. And then I'll take that one off of the stack. And oh, look, there's another one underneath that.
Yeah.
Don't pay attention to any kind of magic that's happening there. Just take that off the stack, that sort of thing. It kind of looks like that. It's like this infinite
Yes.
stack. Ah! Okay, I'll do that later.
And then there are also methods that you can call on stack, such as peep, I think it's called,
Right,
where
peep.
you just look at the top one on the top. Pull, which you take off the
It's
one
pop.
on the top. Pop. Sorry.
No
and then
worries.
push, I believe.
And push puts it on.
Push puts it on.
Right? So here's what we got. Check it out. We've got this command. What we did, and remember this, we used the command design pattern. Remember it's got an invoker? This is our invoker. Our invoker is this thing that invokes the command.
And then there's the, I forget. Sorry.
Oh, you want to see the pieces of it? We were talking about that. Let's go bring that
it's
slide
the
up.
invoker,
Yeah, I think I created a separate slide deck for design patterns. There it is. Here you go. So, this is the piece you'll look for. Yeah.
Okay, and the command.
The receiver is just the thing we've already got. Like, this is kind of what happens right now, what happened before we implemented this pattern. Our client code called the receiver, and it solved the Sudoku, for example, or changed the letter in some place. Right? We just directly called it.
I got results on the hint.
Okay, let's switch over to channels. Like commercial break, kids. What do we got? We got a second hint here.
Yeah.
All right, so now we're going to go to how many solves now?
Now. 1, 2, 3, 4, 5.
Start with 5. Man, that's a hard one. That's a hard one. So this last hit took what, about 5 minutes to get to this point? Did you say 6
I would
minutes?
say so. Wait, it was 42.
Oh, you're right. Yeah.
Yeah,
it's
7
about-
minutes.
It's about 6 minutes. Oh yeah, 7 minutes. Let's do 7. That's about 7 minutes.
Took approximately 7 minutes.
Then 5 solves, and then another hint. Here we go.
Then.
How many? When you're done writing this down, I want to go take a look at the. Before you hit any buttons, I want to take a look at the title bar and see how many trillions of possibilities are remaining.
Probably not as many. 2.
The other thing that I just realized we could do, Campbell, if we solve once to get a hint, every other hint after that. Oh yeah, we're way down. We're down only to like a couple trillion, I think. Let's see this. Oh, wait. 1, 2, 3. I think we're at 1, 2. Yeah, we're less than a trillion combinations right now. We're about, it looks like 85 billion trillion combinations. If my math is right, that may not be. That's what I think we're at. I'm looking at all that right correctly. Okay, so we're stuck here. We're gonna, I guess, hit solve again. The thing I was gonna say though, Campbell, is that once we solve for the game, as long as we don't load a new game, we can do something called caching, which is like storing something. There's a term. This is actually a term that you used to use. I think more in like olden days, like back in Wild West. You used to have a cache of gold. C-A-C-H-E. It means a store of it. You would hide your money in a cache, kind of thing, right?
Okay.
So we can do the same thing here, where once we calculate all the results, we just save them because the board doesn't change. And then next time you ask for a hint, it's instantaneous because we just go to our saved results. See what I'm saying? And then come back quickly. That's another way we can improve performance. So did you hit solve again or no?
No, I don't think
It's about 10, 15 more.
Yeah, so now we do one hint.
Yeah, sorry, hint. Rather, yeah.
Hint.
Did you
I
hit it?
clicked it.
Okay, cool.
No responses yet.
So we'll maybe come back to that. All
right.
Excuse me, back over to this machine over here. So command design pattern. This is what the typical client. This is the typical client receiver coupling. And by the way, when we're talking about our code, Campbell, we're not often saying, oh, this is the receiver. We're calling it what the class name is, right? And we're not, and sometimes we call this the client, but generally we just say it's main window. Does that make sense what I'm saying?
Yes.
Okay. Let's move these down a little bit. So the typical client receiver coupling looks like this. And design patterns are generally all about decoupling.
I got a hint.
You got one?
I got it.
And so what did that take? Like a minute, 2 minutes?
Yeah, not that long.
Okay.
No, not even a minute. I didn't get the break thing.
Okay, sweet. Yeah, so we can do about 1 trillion.
I don't think I'm gonna write down how long it took because I don't think it really took that long.
Okay, that's fine. Now how many solves?
Oh yes. 1, 2, 3, 4, 5.
5 solves. That's definitely an expert game. The question is the new rule that we're coming up with that we implement, if we get it done today's show, maybe tomorrow, is it going to be powerful enough to have any impact on that expert game?
I don't know if it will for the expert game, but I think maybe the medium game and the hard game it will.
Well, I don't know. We'll see.
I don't even know about the easy game. If we can get it down to just 2 presses of solve, that would be impressive.
Well, I'm not worried about the number of presses because part of the other thing that's happening is part of what's determining how many presses, realize we're running 5 rules at every press, right? And it's kind of like what rules happen to be available, right? It's some kind of metric, right? It's kind of a metric that's kind of interesting, and the fewer presses it takes generally means the more rules we're running and the more things that we're able to determine with that rule. It's really a reflection of our deductive abilities in our rules, I think, right? So there's something there in terms of it, but I wouldn't put a huge amount of weight on there because it's not an actual count of how many rules are being applied. We could count that separately, right? So we could have better metrics rather than just simply these. We just say, hey, go solve. You go off and solve it, and you tell me what it took to solve it. Right?
Yeah.
And it could come back and actually write out a document for you like this, as an example. Okay, back over here to my machine. Well, actually, the machine's freed up now. We can go in and start doing the redo. How much code did I write? Let's see, what did I do here? I added the redo method. I almost think I want to do it on your machine. Is that cool with you, Kim?
Yeah.
All right, I'm going to undo this. I'm going to go, what other file was I in? I was over here. I'm going to undo this. Oh wait, I am going to do this. I'm going to copy this to the clipboard. Do I give it to you or do let's do this. Let's actually put this back here. I'm going to check this in. We'll give everybody out a link there. So I'm right here. We just added code. Right here. Added code to. Did you check in your code from earlier in the changes that you made?
I believe so. Let me check.
Wait, what's in the solver 3x3? Click on this. Go over to Kimball's machine again.
Oh, just the comment.
Okay, so just discard that. Perfect. Cool. Back to my machine. So we added code to detect a redo key press. That's what we did.
You might want to list the examples, like Control Y and Control Shift
You got it.
Z, not V.
Control plus. For some reason my fingers are like, yeah, I don't like typing this morning, Mark. Control Shift Z or Control plus Y. Will work. Okay, I'm gonna hit commit on that. Give it a second. If your current branch is behind. Oh, I know what happened. I get it. Because I didn't pull down your changes after you checked it. My bad.
So it's pull.
Let's see if that works. Go ahead and hit your fetch button up there on your machine.
Fetch.
Handles. Yeah, you should okay. Looks good.
Pull.
Go into, oh yeah, there you go. Do the pull. No changes, yeah, just hit pull. Perfect. Perfect. Go back into Visual Studio. It might say new message, so it's reloading. Looks like it's good. Go to, so we've got this thing. I want to see the Solution Explorer. Go into the View menu. Oh, I see where it is. It's off to the right. It's up over there in that corner. So click on the Solution Explorer. Right over
Here?
there. No, but actually you can do this too. I just want to see the command invoker. That's what I want to get to. Bring me to the command invoker. Up near the top. There you go. All right, go down and scroll down a little bit. There should be the redo in here. Okay, we're running, so hit Shift F5 to stop the run.
F5. Not working.
If it didn't work, it may be because function lock was down. Okay. Okay, so let's get rid of the throw not implemented exception. Not throw that anymore. Let's implement something here. Let's scroll up. I want you to look at the existing implementation of the undo stack. And let's kind of think of this visually, I think. When we stack things up,
Wait, why is it pushing if it's undoing something?
it's not undoing in that method. What's that method called?
Undo stack dot push.
No, what's the method that you're in called?
Oh, do command.
Do command. Let's just talk about that. If I tell you to do something, but I want you to be able to support undo, you've got to add to your stack the task that you've done,
Yes,
so that if I say undo, you can go to the stack.
To the last one. Okay.
Right? So what's happening is when I tell you to do something, you're going to say, well, I'll do it. That's line 14.
Yes.
Right? Command.execute.
And then
Line 15 is, I'm going to remember this for later.
pretty
Right? You good with that?
Yeah.
Okay.
And then in undo is where we're declaring what to do. But then where do we call undo from? Let's see. Command.
When we press Control Z.
Alright. In
Okay.
mainwindow.xaml.cs.
What'd you say?
In mainwindow.xaml.cs.
Okay, if you can't go back to main window, did I make sure? I want to make sure I have handles equal to true under the redo call. Looks like I did. Right down there. That's what I was looking at right there. Okay, go back over into redo, or let's go to undo. So let's scroll up just a little bit. Get line 12 on screen. Yeah, there you go. So look at the do command. When you do the command, you not only do it, line 14, but you do something else on line 15. What did we say that's doing?
Wait, we are
Oh, bless you.
remembering what we did before, basically.
We're remembering what we did before, right? So when we undo something, if we need to redo it, should we maybe have the same kind of logic there? Because in order to redo, how would we be able to redo? If we pop it off the stack, it's gone forever.
Yeah. So when we pop it off the stack, we have to put it into another stack. Right?
That's exactly right.
And then in redo, we have to take it from that stack and put it back onto the.
Really, really nice job figuring that out. That is not an easy thing to figure out, but that's exactly what we have to do. We have to come in here and we have to create a redo stack. See it?
Yes.
Now, when we undo something, there's our command right there. See it?
Yeah.
We popped it. We're going to come in here and push it, just like you said. Right? Boom. Not bad. What happens? Is there ever a time when my redo stack should be... I guess there's two ways to empty my redo stack, is what I'm saying. I was going to ask if there... But let's talk about emptying it. So let's write this code right here. For the undo, for the redo, I'm going to say it's based on this. Okay? Would you agree that the logic for redo is similar to this?
Yes, very similar. I think we might even just copy and paste it.
Okay, what's different?
Well, we aren't pushing it onto here, right? We're popping it off.
No,
And-
stop. Kind of, but don't make the change
We're
there.
popping it and then we're pushing it back onto the undo stack.
Right, so instead,
Oh.
there you go. There you go. And then what about line 32 and line 30? What are those turned into?
Well, line 30 is, it's not this, it's
Perfect.
redo stack, yep. And then 32 here is also just redo stack.
Yes. There you go. So now what's happening is when we hit redo, we check to see if the redo stack counts 0, and then we just get out, because we can't do anything. But if redo has anything, we pop it, we call, we call undo, or is there's just a command.execute. See that?
Yeah.
That's the forward direction. So we'll say command.execute. Right there. Well, look who's here. Copper Beauty. Took a shower already, man. How you doing, Copper Beauty?
Hello, Copper Beauty.
Copper Beardy is in the house.
So Copper Beardy, Campbell and I live in Costa Rica, and so we don't really have seasons here. We have like a rainy season that lasts a couple months, and then a dry summer season.
And we kind of have a sub-season of dry season. It's called fire season.
Okay. Yeah.
Where, you
So
know.
what's the weather like where you are right now? Sometimes when I talk to you and like it's got snow on the ground, sometimes you're growing sunflowers. What's it like over there, Copper Beardy? Interested to know. Okay, so we are working on, Campbell and I are working on an undo and redo. We've just added this, which I think is going to work. Okay, we're calling command.execute here. But I have another question. When does the redo stack get cleared to empty? It gets certainly cleared if we redo enough times. But the question is there any other time? And so like the idea is, let's say I type in 1, 2, 3, and I hit undo, so now I've just got 1 and 2.
Yes.
Okay? My redo stack has a 3 in it,
Uh-huh.
right? What if I hit a 4? What if I manually enter a 4? Should the redo stack keep the 3?
I think it should keep the 3, but the undo, yeah, it should have the 3 on the bottom and then the 4 right there.
Okay, so it keeps it, and then, well, it doesn't have a 4 yet because I don't have it undone anything. I can only get things in the redo stack if I undo something, right? So let's see what happens
Oh,
here.
so wait.
Watch, let's see what happens here.
Well, are you saying that if we have a 1, a 2, and a 3, and then we undo 3 and manually enter a 4, and then we hit redo, what would happen?
Yeah, that's kind of what I'm going to say. Yeah, so look at this. I have a 1, enter 2, enter 3. I'm going to hit undo, redo. The 3's still on the stack, right?
Yes.
If I hit redo again, it's going to go there. If I undo, it goes back to the redo stack. Redo, it takes off the redo stack's empty.
Yes.
Right? Because I can't redo any further than that.
And
Undo, hit the 4, or the 6 I did instead. Now when I hit redo, nothing happens. That 4 doesn't come up. I've broken my opportunity to redo because I've entered something new. That's the way it is implemented by and large everywhere. If I were to keep that, it kind of almost doesn't make sense. It's a little tricky for the human mind to make sense of all of that.
Yeah.
Why am I able to redo when I haven't undone? cover reader says very sunny day today. Usually we have one season, wet. Got it. Got it. Okay, so we need to clear the redo stack when we make a change. Where are we making a change when we're going forward with something new? Which one of these three methods, do command, undo, or redo, are we going forward with something new?
Wait, sorry, can you say that again?
Yes, we need to clear the redo stack when we type something new. We've just seen that that's how
Unless, wait, only if we type something new in the square that we undid from, right?
No, because it's not, this is undo globally across the board. We're gonna move around and change squares everywhere.
So if we load game and then hit solve, and then we hit undo, and then here, or not even here, if I enter a 7 here, or wait, sorry, if I enter a 3 here, so that there are no errors, are you saying we would not keep this? Oh. Yeah, no. Oops.
I didn't know you could put a Y in there.
Sorry, I meant to. Wait, you should be able to.
Maybe we have a bug we added, but I'm sorry, I'm still trying to understand the question.
So, if I'll just do it again. Wait. So if I hit solve, right, and then I hit undo, Control Z, and then I enter something here, are you saying when we hit redo, it shouldn't be able to?
Right, there's no forward direction once you break the redo stack. You break the redo stack by entering something new.
Control Shift Z isn't working.
Can I try it?
Yeah.
Okay, let's try it. So 1, 2, 3. Undo, redo. Right, you're right, it's not. The
Only
Y is working.
Yeah, Y is
Control
working.
Shift Z is not working. Control Shift Z, why am I? Maybe
Neither
it's a
does
problem with
Shift
our
Control
code.
Z.
Maybe it has flag. I think I need to do this. I think the problem is in my code, Campbell. I think both of these are returning false because it has more than just that. I think I have to do this. This is called a, no, that's what I thought. Oh, because we're running, right? Let's try now.
Yeah.
All right, so this is a bitwise OR. Holy cow, what does that mean, Dad? What that means is that it's looking at the individual bits, the zeros and the ones. And so if I have two zeros in both of those at the same place, it'll be a 0, because 0 or 0 is still 0. But if I have a 1 in either place or both, then it'll come back as a 1. That's essentially what it means. It's kind of like a math, it's a bitwise math problem is essentially what it is.
It kind of compares.
Yes, it's like a comparison, but it's an operator.
It's like what are they called? Oh, I forget. But you know the things, it's like, it's basically the simple things in math that is like, if this and this, then return this.
Like an axiom kind of thing.
Yeah,
like
if this is more than this,
right.
then
yes,
don't return.
It's like a comparison operator, but it returns a value.
Yeah.
Comparison operators that you
What
some
are
of the
they
ones we talk
called?
about.
I think they're called Boolean operators, but
Boolean
that doesn't
operators,
seem right.
Yeah. It's like a Boolean operator, but when we say bitwise, that means it's changing a number down inside the computer somewhere.
Or like if this variable is true and this variable is true. Yeah,
Right.
basically, yeah.
Now, yes, exactly, yes. So now this symbol is not something you encounter a lot, so it's not something you really have to commit to memory or learn about right now, but that's, I think, going to be the fix to it. With it running now, let's try this out. Let's load a game. Let's type in, let's go here and say 1, 2, 3, undo, Control Shift Z. Interestingly, Control Shift Z got forwards, but not backwards.
Huh.
It got forwards 1, but not more than 1. I'm sorry, I totally didn't say that correctly. It called it execute, I think, but didn't have the rest. Is that we are pushing the redo stack there? Let's see why that's not working. let's try it out. All right, so we're gonna say 1, 2, 3, undo, undo, undo. I'm just gonna hit Control Y for a second. Control Y, Control Y, Control Y. So Control Y is working. Control Z is still. It was Control Shift Z that was having problems. Undo, undo, undo. Control Y, Control Y, Control Y. Undo, undo, undo. Control Z, Control Z, Control
Control
Z.
Shift Z.
Yeah, Control Shift Z. That's what I'm hitting, and it's doing nothing.
Wow.
So it's not that. I think there's a problem with this. I think the problem is it's not detecting the Control Shift Z is pressed. So I think there's a code here, a problem here. Let's go. Let's go to the internet and see what the internet has for us on this. See what we can figure out here. So I would definitely expect one of those two to solve it for us. Open up a new Google Chrome instance. And we're going to say C#, WPF, keyboard, dot modifiers, dot has flag, and I'm just going to type in Control plus Shift plus Z. Control plus Shift. And just Control and Shift. See what happens. Interesting, they're saying use keyboard.isKeyDown. Let's see what's going on here. Let's set a breakpoint here. And I'm going to hit Control Shift Z. Where is it? Is it on another screen? Can you drag it over to this monitor?
Yeah. It's not on another screen, but it's just. Here, let me shift F5. Oh yeah, that's shift F5.
You started it up again? Lose it, that's right. Hold on. I just had it up for a second. Well, I had it up for a second, now it's gone. Did you hit the solve button?
I didn't.
Let's try this. Do I recall?
Yeah.
I think it's solving. I think it's doing a, I mean not a solve button. I think it's in the middle of, yeah, I think it's in the middle of solving.
Brute forcing?
You hit the call stack? Yeah, it's a brute force attack was
Oh.
That's what's going on. Okay, so let's go run it again. I just wanted to get Control Shift Z, like right now. I'm going to hit run here a second. I just got both the control and shift key down. Well, it keeps coming down here. Well, let me hit all of them then. Okay, here we go.
I think
What do we got? Key is equal to Z. Keyboard modifiers have flag. Let's copy this. And let's put this into the watch window. Let's add a watch for this. And it says it's true. It's true. We're invoking it. We're saying handled. Okay, so our code is good. I think what's happening is we're seeing the same problem that we saw before.
with it's redoing our redo, but then wouldn't it just?
I think it might be with that what it's doing is it's redoing the redo on that is what it's doing. But let's do one more check. Let's just make sure. Let's go back to our command invoker, and I want to make sure that when we hit that redo, I want to make sure we don't get in here. That's what I want to make sure we don't do. So let's have to prove breakpoint in a second. Let's just do a 1. Do that.
Wait, but if it's redoing our redo, we're not undoing anything.
No, I think it might be just clearing things. I'm not sure. So I did 1, 2, 3, undo, undo, undo. Now I'm going to set my breakpoint, and we've got something in the redo stack now. We'll set a breakpoint here on do command and on redo. See if we stop at either of these. So I hit redo. Here we go. Redo stack is equal to 3. Run it. Good. There should redo something. Redo again. Redo stack is still equal to 3.
No, but it redid the 1, didn't it? Or did we did we just not undo that?
Well, let's see what's happening here. Command is equal to redo stack.pop, text change command dot execute, undo stack, push the command, good. Redo stack's now at 2.
Oh.
Hit it again. Redo stack is back to 3.
Oh. No.
Oh wait. I think undo is getting called.
Oh, because it's detecting. Oh, we also have to have okay. I think I know how to fix it. So, I think what we have to do is wait, which one is it in?
Main window.
Okay. Yeah, no, here.
Dot CS.
So, here, undo, and, oops, wait,
You do that after this expression if you
Yeah.
want.
and,
Put a space there so you get the template expansion for you there.
and what?
Or you can also take that and shift enter on it.
Oh,
We'll do that. You do the modify, operator between the two. Alright?
shift, yeah, shift, and then,
Try it. Save it and run.
S, close,
Try tapping all your control keys. Yeah, all the modifier keys on there. And hit control S key to see if it comes up. I think this is intercepting the wrong key. Does that help at all? Control S now work? It's still not saving.
Oh,
Just hit the
it's
save
still
button
in
up at the
Skype.
top.
Why did it open Skype? Control F. Okay, that did.
Alright, so let's try it. Load game. Put like a 1, 2, 3. Yeah, you can get rid of all these. Put all the breakpoints. You can do that once easily from the debug menu if you want. They're only 3, so no big deal. Go to F5 to run or continue. Hit to run.
F5? F5 isn't working.
Okay.
And now we can control Z. And then control Shift Z. Yeah. It worked.
Wait, let's try it with 3 numbers. Let's type in 1, 2, 3 in 3 different places.
So now 1, 2, like this.
Yeah, and now hit undo, undo, undo,
Control Z, Control Z, Control Z.
and then redo, redo, redo.
Yeah.
Okay, you fixed it. Congratulations, Campbell. That was awesome. That was like your first, I think, full-on all by yourself. I think I understand the bug, followed by I'm going to go right here to fix it. Right? You've come a long way since the start of this, right?
Wait.
What?
So here. Oh wait.
If you're looking at hints that are wrong, we don't have anything that checks to see what things we've just typed in. So it doesn't change the hints automatically. They're only done when you click on the solve button.
Okay. All right.
Okay, you want to get the focus in the right spot? That
Yeah.
That,
So that when we click,
indicator?
it selects it as well.
Okay, so let's do it. Let's start with the clicking part. Is that cool with you? Okay.
We
so,
did that in mainwindow.xaml, right?
Right. You
Was
want
that
to
CS?
go to mainwindow.xaml. Let's start there.
Okay.
I'm actually trying to think about this in terms of what the best way to do this is. We're basically looking for a mouse down somewhere in here is what we are looking for. I actually think it's in the square itself. That's what I think it is. So I almost want to go actually not into main window, but in our
Sudoku square.xaml?
Yeah, and then so I can just right click, see this .cs here?
Yeah.
I can right click and choose View Designer, and that'll take me to the XAML.
Ooh.
I think this is where we want to be. And I kind of think I kind of think it's related to this got focus here. See this got focus event? Let's see if I can get it out. Yeah, let's see it. Where are you, got focus event? It's right there.
Yes.
That's the got focus event. Right now, we just call save last value. That's the only thing we do on the Sudoku square. But we could create a new event when this happens to say, hey, we just got our focus.
So change the selection.
Yeah, that's kind of what I'm thinking about doing. So let's do that. Let's come in here, create a new event handler. We're going to call this got focus. And we're going to subscribe to this. We're going to listen to this event from outside the square. So events are just a way of communicating from one class to another, or from one instance of a class, rather, to another, right? So I can have an event on a cookie that says, somebody taking a bite, right? And then I can give you a whole bunch of cookies, and I can listen to all the events in all those cookies. And as soon as you start taking a bite at something, I can do some sort of practical joke, like play a fart sound or something like that, right? You take a bite and you like that, right?
Yeah.
I could do that because I've got the events and the cookies are speaking to me. You know what I mean? You know what I'm talking about, right?
Yeah, it says, oh, a bite has just been taken.
Yeah.
So do this.
Yeah.
Or it just says a bite has been taken, and you're like, oh, if a bite has been taken, I'm gonna do this.
Yeah, I'm gonna call this square got focus is what I'm gonna do. Square got focus. Only square receive focus. That would be the language there a little bit better.
Yeah, I think you need to rename it instead of just.
Square, you think I need, instead of changing it, I need to rename it?
Yes.
It's the only one now, I just added it, so I can kind of take a shortcut. But you're right, a rename is definitely a safer way of
Sorry,
doing it.
I thought that you took it from the other class.
Oh, I see what you're
something.
saying. No. What I'm going to do though, what I'm going to do is I'm going to trigger that event. I'll be triggering this event right here. Let's see. Oh yeah, we got a trigger for it. So coders can create an event trigger for you, which you can do like this, and you just put it where you want to put it. Put it right next to this event trigger here. So on square receive focus, like that. And then anybody's listening to it will call invoke on that. It's a little bit similar to a command invoker, in that it's just going to go, hey, look, this question, the question mark here says, hey, is anybody listening to this event? If anybody is, then we're going to go invoke those listeners. We're going to let them know that somebody, the squares receive focus, or that somebody's taking a bite of the cookie, or something is happening that we want to know about. Okay? We still have to call this to trigger the event. But the cool thing is CodeRush writes this code for you here, so you don't have to. Now all you need to do is call on square receive focus in the right spot. Well, we are listening to the, what is it? It's the, it's going to be this long. There it is. We're listening to the text box's got focus command. When that happens, we're going to go and say on square, we're going to call on square, we're going to call it receive focus. We're going to pass in this, we're the sender, and I'm going to pass in EAE, which stands for event args empty. In other words, there's no additional data. Event args can be additional data, custom data you want to pass to the event. So you can have incredibly sophisticated events that pass incredibly sophisticated data, or you can have simple ones like this that pass nothing essentially other than the square that we're in. This means when I see this here in the code, that means it's this instance of the cookie or the Sudoku square, of the game board, whatever it is. It means it's this one. Okay?
Okay.
And sometimes I can use this as well to say I only want to access something here locally. So I can type in this dot, and you now only see methods on with this. It might help you define that allow drop method. You don't really need this to call allow drop, but you can use this dot to find it. So this means it's this instance. Okay? So we're passing in this instance, no event args, right there. The last thing remaining is we need to listen to this event. Well, I want to go check it. I'm going to tap to next reference here to see where are we hooking it up. That's where we're hooking it up, right there, in this cool method called what?
Called Sudoku. Wait.
What's the method?
Hook events.
Hook events. Who named that? They were a genius. I'm not saying it was me, but if we are hooking events in the hook events method, I'm saying it was me. I'm that genius, man. I named it. I came up with a great name. So what we want to do here is we want to hook in addition to the value change, we want to hook the other one. So we want to go in here and hook the other one. Now right here, remember I can tap control for options.
and then you can like say you only want properties or
your events, right? And now I've got that. I can also come in here for options. I can hit hierarchy and say only the Sudoku square.
Ooh.
Only
that's
0.
cool.
Then go back in and look
I
only
forgot
for
about
events,
that.
and now look, I only see these 2. Does that make sense?
Yeah.
So I can choose where I want to look in the hierarchy. So we went square receive focus. We type in plus equals, then we hit tab, and Visual Studio is going to give us the rest of that code right there. Sweet. So now we've got something in our main window example that says the main window square receive focus. And guess what sender is? We can ask, we can say, hey, if sender is by chance a Sudoku square,
At the time,
then we can give it a variable name, Sudoku square. And now inside here, we can call all kinds of methods on Sudoku square. Like for example, we can call, I think what we want to do is say this. We want to say, hey, look, the selected square, I thought we had a selected square. Do we have a property called selected square?
we do.
Wait, let's see, let me type in selected again, let's see what I get here. Select, I got
Selected square. Select. Oh. Right.
That's a method though.
Aw.
What happens in select square? What's going on here? Let me go find out. F12 to jump inside. Oh, it's inside Sudoku board. We moved it. We used to be here, but we moved it. So now what I'm going to do is I'm going to say selected square is equal to the one that just got focused. And I think that's going to take care of our highlighting and everything. I think. Okay? I think we're done.
Okay.
That's what I think. So remember the sender? So just to show you again, we're over. We're here. The text box just got focused. Maybe you clicked on it, right?
Yeah.
Okay? We do this, save last value, whatever that's for, I don't remember anymore. But it's needed somehow. We can tap the excerpt because we want to investigate it. Then we call on square receive focus, passing in this. This is the Sudoku square. Remember? It's
Yes.
this instance. On receive focus, what does it do with the sender? It's now in that so now that this is in the sender position, and we call invoke. Invoke is going to come out and it's going to go to this guy, passing in that Sudoku square as the sender. We're going to check to see if it is in fact a Sudoku square, and if it is, we're going to put it in this variable, and once it's in that variable, guess what? We're going to just say select the square is equal to that. I think that's going to work. Let's try. Go ahead. Click. You can click anywhere now and see if it would work.
Yeah.
Ah, better.
And now, yeah. And then I can click back in.
Cool?
Yes.
All right, now type in 1, 2, 3. 1, and then next to it, and another one, 2, and then 3. Or fine, 4. Hit undo. Hit undo. Okay, hit undo again. Not redo, undo.
I did.
There. Hit undo. And again, what? Look what happened. Do it again. 1, 2, and 3. Why are changes happening in other squares than the one you're in? Watch it. Hit undo. Fine. Hit undo again.
Wait, sorry. I am hitting undo. It's just because.
Oh, maybe you did a 4 and then a 3.
That's what I did before.
I got you. Okay.
Here,
I'm
I'll
sorry.
just do it again.
That's totally my fault.
1, 2, 3.
I know. This is me.
And then control.
Do it right. You're like I am. You're the one who's wrong.
Control Z.
See what's happening? Shouldn't the focus square move?
Change to here when you hit control Z.
Does that seem to make sense? Because your eyes should be looking and guided. You should guide your eyes to the right place instead of forcing you to figure it out.
Yeah.
You agree?
Yes.
Okay, so let's figure that out. Can we do that? Let's go look at undo and redo in the command invoker.
Okay.
See if we have what we need. What we need is a Sudoku square to get focus to. Command invoker's up to the left of, in the tabs. There. Do we have a square? What's in command?
Let's see.
Inside the class command, I mean. What has it got?
This is in text change command.
No. Yeah, well, we can look at. It's only got execute and undo.
Wait, we want redo in here, right?
No.
Okay.
Execute is the forward direction. That's what we call when we redo.
Okay.
All right, let's go. Let's go look at the descendant of command. So if you go up, put the caret on command. So I think I've shown you the hitting num enter, right, to go find things.
Yes.
If you hit the delete key on the numpad just next to num enter instead,
Oops.
click on command and hit that delete key down there, the dot delete. Now go to derived types. Those means descendants. Okay? Hit enter on that. And go to the text change command. Just a fast way of finding who's descending from it. Well, we do have a row and column. We don't have the Sudoku square, but we have the row and column. Scroll down. Anything else? Any other properties? Anything else with a crescent wrench next to it? No? That's it. All right, sweet. Okay, so what we want to do is we want to use that. We have to first check to see if the command we're executing is a text change command. Oh no, maybe we don't. Hold on. We don't. All we do is here. This is where it goes. Sudoku board dot select square. Oh, selected square. Oops.
Yeah.
Equals. You know what I want? I want to create a method. It's called select square. Row, comma, column. Right? Doesn't that feel better? Right there?
Yeah.
Select square there. And then we want to do the same thing on the undo. Does that make sense?
Yeah.
So this will be called, when we do it the first time, by hand, and it'll also be called if we redo. And this one happens whenever we undo. So we're just going to highlight the column that we're making the change to. That feels right. It makes sense. I do have a select square method. Thought I did over here.
We do.
I thought I had to select square. Let's have an X reference on this guy. Select first square. There it is. That's select square. See this? What I want
Yeah.
is I want to put this down into the Sudoku board. That's what I think it was. I want to call that same. I just want to call it there. Like this, and then all this code is going to go down there into it. All right, with me?
Yeah.
And down here, we don't need these classes. We don't need this preface with. Let me show you what we have here. Before we had this, because we were outside the class, we had to say, hey, go inside Sudoku board, and I mean the selected square in Sudoku board. And I mean the squares array in Sudoku board. But now because we're in it, see right up there, we don't need that. And see how the Visual Studio's dimmed them down a bit? That means you don't need this. Now we can just there. It just makes the code a little simpler. If you put things where they belong, the code gets simpler.
All right.
Does that make sense? All right, now with that change, I think it's going to work. Try that as a run that and see what we get.
So now if we hit, and then we do, yeah,
It's much better, isn't it?
much.
Right? It's feeling. If our cognitive load goes down, we're on the right track to making it better.
What? I'm like here. Oh,
So
another
that was-
great thing is, watch, look at this. If I have my selection here,
Yeah.
and I hit load game,
Yeah.
wait, if I hit load game, oh wait, I already did. Oh, wait, let me just. If I have my selection up here, and then I hit load game, oh, never mind. Oh, wait, sorry. And then I hit solve.
Yeah.
Look, it brings me to the last thing that it solved. Which isn't like really needed, but it's kind of cool.
No, I think it's cool. I think that is cool. Right? Especially if it only brings in, there's only one that it got there from solve. That sort of, it only finds one that you fully see that. Yeah.
Oh yeah, wait.
If you hit undo, you should be able to undo the solve. Is that true? And then redo
Yeah.
it. Can you solve all the way to the end?
Oh, wait a minute. I want to see something. If I solve all the way to the end,
Now undo and then redo.
and then undo all the way to the beginning.
Oh, it's undoing one at a time.
Yeah, it does that. It's super cool. and then I redo all the way back to the end. Oh, that looks so cool.
Yeah, you should be able to go back and forth, right? Because if we're careful about the way we design this, right? The thing is, once you go all the way back here, here's the example of destroying the redo. Type in anything here. Anything. Now try to redo. You can only undo and redo this point. Do you understand what's happening? And this is true in all the apps.
No.
Wait, what? What?
I don't get why we can put in letters here. We shouldn't be able to.
Yeah, I don't either understand that. You do it. Hold on a second. I'm trying to investigate why did the other one just happen. We do the 3. I can undo the 3. But if I go forward now, I should be stuck.
Nope.
Wow, I'm not stuck. How is that not getting? We need to go check that because we're getting.
Well, it's cool. Isn't it good?
I don't know if it's useful or not. What we're looking for is, oh, you know why? Because we never added the clear. That's why. That's why we have the bizarre behavior. What we need is when we call do command, we need this code there. We need to call clear when we get into do command. And then that way we won't have this extra. Because the problem is your redo stack just keeps growing and it becomes disoriented, right? Where you're now adding things to the redo stack as you undo. And now where are you now? Under the redo stack? It doesn't make sense. If you're not traveling through time anymore, it's kind of like a time loop where you're taking a jump across time. And then you take another jump across time every time.
And then you want to go back to the first time you were.
Yeah, and you're building all of a sudden a time flow that doesn't actually match up forward to the beginning.
Yes.
So with that change right there, let's see if we can now. I'll just restart. That's what I'll do. So we've got the redo stack clear here now, and now let's run it. And that's cool because now we've got undo and redo. This should now work. So you load a game up. Solve it to the end, undo all the way, redo, undo all the way, then make a change, try to redo, you should be stopped for.
Control Y.
And then undo all the way again. Now make a change,
Make a change.
and now undo it, and then try to redo, and you can't go forward down that other path anymore. Because the other path is gone, right? It's another branching direction of time. Does that make sense?
Oh, so if you go forward through time, then you go back to that time, and then you go like to the side in time, if that was a real thing.
Right, that's what's happening. You're creating a separate parallel universe, right?
Yeah.
And what happens?
I guess you wouldn't go to the side in time, but you make a decision in time that like branches off in time.
Exactly.
So that if you control Z, so that if you go back in time and then go forward in time, it will always be in that reality. Like
right.
in what is it called? The movie.
Some movie we saw.
Yeah,
Time
but
travel.
but like with Doc and Marty.
Back to the Future.
Yes, I don't know why I couldn't remember that name.
That's
but
alright.
Yeah.
Well, you're getting old, Campbell. Your brain's not working as well as it used to.
But you know, in I think it's the third one. No, in the second one, the older Buff, I think is his name, comes back with the sports book, and then it branches off into reality, and then he tries to go back in time and fix it.
Right. That's what we're talking about. Yeah. Copper
Or
Beauty
he-
says LOL. Copper Beauty thinks it's incredibly funny.
Yeah, because Marty goes forward in time, and then he goes backward in time,
Yeah.
and then he goes forward in time again, and it's
Right.
Yeah.
That's what we're talking about. So when you talk about undo and redo, if you're thinking about time travel, undo and redo only work within one universe, right?
Yes.
And I branch to another universe once I go backwards and I make a new decision to go forwards. That's the branching point. And that's what happens when we destroy the redo stack. Now, would it ever be sometimes useful to store all these multiple branches and make those available? Maybe. But in my experience, most humans, including myself, have a hard time understanding which universe I'm in, right? If that were to be presented,
Yeah.
right? You know, and it would just be confusing. So we have to have a way to disambiguate the confusing parts and to visualize, to help the user visualize where they are. Because say, for example, you're writing a bunch of stuff, you're creating like, you know, you're creating a document like your resume, or for example, and you put in a bunch of data, and you just finished typing in your address, and you realize, oops, I spelled my name wrong up at the top.
Oh.
So I'm going to undo, right?
And then put in your real
Fix your name, and now
And
when
then
I
you can't
go forwards
redo.
on the old track that I had when the name was misspelled.
You can't.
I can't do that, right? So the question is, how do we do that right there? Grandfather paradox, says Copper Beardy, which is, I think, the effect of saying if you go back in time and kill your
You
grandfather,
can't. It's impossible.
yeah, what happens to you? Well, I think your grandfather. First of all, you go to jail because we don't do that stuff here, man. All right. So I think here's the thing: we have got 20 minutes left. Although, in fairness, whatever you want, you can do. You want to try the next thing? You want to try the next thing? Stop right at 12. Try the next thing. Keep going till the police come to shut down our show. We can just save the next thing for tomorrow. It's kind of a big, heavier thing, and I kind of feel like we're at a good point. So maybe this is a great point.
I think we should. I want to do the big heavy thing, but I'm assuming that we won't finish it by 12.
Yeah. The problem is, like, if I had to do it by 12, I could maybe do it by 12, but I'd go really fast, and that's not fair if anybody's got questions, right? And so I don't think that makes sense. You know what we can do if you want? We can talk a little bit about how we do it in code, how we would solve it.
All right.
Talk about the rule again, and just kind of wrap up with that. Is that cool with you?
Yeah.
And then that gives us a mindset for tomorrow's show. That's what we'll do tomorrow.
I can't believe we had like pretty much every rule or a ton of rules in Sudoku. We even had the brute force, but we still didn't have the only one solver rule, which is kind of just like the base on which most people do Sudoku.
No, I think we do have that, but we don't.
Now we do, but before we didn't.
We didn't have it before? Let me go back to your machine because I'm trying to remember.
We didn't have the only one solver, which basically says if there's only one note here, then
Yes, right. We created something actually specifically called that. Only
only
one
one
solver.
solver, yeah.
Yeah.
Which basically says if there's only one note in this one box, if there's only one note in a box,
Yeah.
then just put that note there.
Yeah.
We didn't have that before.
Yeah.
We had if every other thing is blocked, then don't do that.
Yeah.
But we weren't really looking at the things.
Now, there's a couple cool things here. Now, I know that you're like a totally new programmer, Kimball, but as an old programmer, as a guy who's done a lot of coding, there are things that may not be easy to see here about this, and I want to just note them just real briefly. One of them is that there are two aspects to our design that are really, really, really good. One of them is represented by these lines of code here, where we've decoupled our solvers from the engine that does the solving. And we did that with an ancestor class. All of these classes here, I'm pretty sure, if we go look at these, if we like tap the next reference, they all descend from the base group solver, right? See, look, the solver n by n descends from it, right? And our list of solvers is just these base group solvers. That's should be an abstract class, pretty sure. Yep. Meaning I'll never create a cookie out of this thing. I'll never create a real instance.
Yeah.
I keep using cookie as my representation for an instance. So that's a really, really good architecture. That means if I want to create a new solver rule, right, just like you saw this, I just added these into the list, and the program said, you know what, you give me more solvers, I know how to solve with a solver. Bless you. Right,
We
so
might even consider calling the only one solver the solver one by one, because that's kind of what it is,
yeah, we can do that. Let's do that right now.
more or less.
Rename. But it does not descend from an n by n though.
Oh, right. So yeah, maybe we just keep it at only one.
Yeah, maybe we'll keep it as I'm kind of with you on that. I was like kind of yes, and then I was like, well,
Not really.
it's a little bit different. So that's very, very cool, right? This is a very cool part of the architecture because it's flexible, easy to add new things. The burden on programmers is low. It's not hard to understand,
Yeah.
right? That's what's going on there. So I love that. The other piece that I love about this is the implementation of the command design pattern. By decoupling our commands from the connection of our command execution between the client and the receiver, by decoupling that, pulling that apart, we were now able to add undo and redo, right? And if we wanted to add command logging, we could do that too. And if we want to create a new kind of command to do something, like think about the solve command. Right now, so you hit one button to solve, and you undo with 20 buttons, 20 key presses,
Yeah.
right? We could create a new command that's the multi-value command and add it into this whole thing seamlessly, and we'd still have a single undo step and a single redo step to the solve as well.
But how would we know how many to undo?
We would change the command. I'll show you how we do that. It's the text change
Oh, do we just log, like every time we hit solve, we remember how many values there are, and then once we hit solve again, and then if we try to hit undo, it will be like, oh, just
Right.
go back to how many values we had before. And those
Yes,
values.
similar. Yes, it's like that. So here, notice text change command. See it? We're
Yeah.
storing what changed and the previous value. Okay, that's what we could do and undo, and here's where we're going forward. Those are both strings. Well, we can create a new descendant of command called, board change, and we could store a whole bunch of things like this. A whole bunch of text change commands inside of it, and then we just execute all of them. So we could do that. We just changed the data that we store, so it's not really that big of a deal, right? Adding these, if we wanted to do it, we could do that. That's the cool thing. Okay. Back over to my machine. So we're talking about this space right here. We were talking about this earlier on the show. For folks who come in just a little bit later, this is a new rule. And I think what I'm going to do, because this rule actually needs data that is also needed by the 3x3 and the 4x4 and the 5x5 solvers we already have, my intention, my strategy is to add this rule to those existing solvers. So those solvers are, in fact, let me just, I think I'm going to actually start typing stuff in. Let me think about strategy here. Strategy. I want to add this logic, add this new logic to the n by n solver. I want the logic, well, let's just say, what is the logic? It's going to say, hey, works when the group is a row or a column. There's also, by the way, so I'm calling this like conclusion leakage, right? And there's also a reverse that goes from the block out into a row or column if those n squares are all in a row, and that impacts only 3x3. You can only, well, no wait, it impacts all of them, all the rules. But I'm not working on that now. I'm only working on the leakage from the conclusion leakage from a square or column. So works when the group, I'm sorry, not square or column, row or column. When the group is a row or column, then we have potential leakage. We're going to apply the logic. The logic is going to, if we find, well, I guess we'll break it into pieces. We are going to group the squares, the found squares that the n by n solver found. So let me just show you what I'm talking about. What I'm going to do in here. You go to the n by n solver. Solver n by n, not here. There it is right there in the Solution Explorer. Here, see that? We have n squares that all contain n nodes or fewer. This is our magic entry point. At this point, we want to add the new logic. In fact, I can already write one line of code here for the new logic, which is if group kind, whoops, sorry, not what I wanted. If group kind is equal to group kind dot column, then we shift enter, or it's equal to group kind dot row. Now I've got a group, a column, or a row. That's This works when the group is a row or column. I just added that line of code. Okay, and then we want to. Now we've got the found squares. The found squares are, where are they? Right here. All numbers found. We've got, what are we doing here? There's got to be an add there. All node numbers. All node numbers is there. So we're going to basically then, we need to kind of go through these numbers here. All node numbers. And Got to figure out more code here. Basically what I need to do is I need to group the found squares by block. That's important. So that's what we're talking about visually up here, where we say, you know, the different blocks, B1 through B9. And we want to see where those squares are, which of those blocks they fall into. So we group by block. So we say to do group by block. Then I'm going to say to do another to do down here. So we got to do that here. Group those together by block. Then after we do that, we want to do we have more than one block? In other words, are these 3 or 4 squares, whatever, do they span more than just the one block we're in? If we do, then there's something we can infer. Do we have more than one block? Yes, it's magic. Like that. That's awesome news. If we have more than one, then we do have another to do that we're going to say do essentially set subtraction. We're going to subtract the numbers from one block from another.
Oh.
So let's say e.g. like B1 minus B2.
Okay.
And there's no negative numbers in set subtraction. There's no negative numbers. So if it's just that I'm just looking at set subtraction to do anything left over. Is there anything left over? If there's anything left over, then that implies whatever the number we started with in the subtraction, right? It's basically it's essentially the target minus the source is essentially how you can think about this. That means there's none of those. If there's anything left over, there's
Wait,
none of
what do
that.
you mean the target minus the source?
Well, so often in subtraction, so if I like say, for example, if I say, what is 5 minus 3, right? It's another way of saying, hey, I'm at 3 and I want to get to 5.
How many
My
do I
target
have
is
to
5.
add?
What do I have to do to get there if I'm at 3?
Oh, okay.
So I'm the source, that's the second number, and this is the target. That's a way of thinking of it. So 2 minus 5 is equal to 2. That means for me, if I'm this guy at 3, I need to add 2 to myself to get to 5. Does that make sense? So here, same thing. This is the target, B2. So I just think, it doesn't matter, we're going to switch targets both times. We're going to say target minus source, and then this time B1 is going to be the target, minus B2 being the source. And in that case, if there's anything left over, that means there's none of those in that square, in that whole square. I'm sorry, in the whole square that are not this one, the one where the piece was. So does that make sense? In other words, look, in this example we have here, look, we have 1, 2, we have a 2, 3, and a 1, 3 here, right here. What that means is if I subtract B2 from what the B2 numbers, which are, we collected them all as uniquely, 1, 2, and 3, subtract from that the B1 numbers, right, which are only 1 and 2, and I get something left over, then that means there's no 3s in any of the other B2 squares, right? There's no 3s anywhere else. When I say any other, I mean any other than these two. We know 3s can only be in these two and nowhere else. So if I have any notes that have a 3, we kill them all. We get them, remove them, because we know now from these 6 numbers that the 3 has to be in 1 or 2 spaces.
Okay.
Does that make sense?
Yes.
That's kind of what the rule is.
Sorry, I have a question really quickly. For our 4x4 rule, does it work if I have like 4 here, four of the digits here, 3 of the digits here, and 2 of the digits here, or no?
Yes, it should totally work. And right now, a 4x4 rule works in that scenario. It just needs to have 4 shared among 4 different squares.
So even if it had like 1, 2, 2, 3, 3, 4, 4,
and
5?
1, 4, yes. Not 4, 5, but in 1. Wait, we got 1, 2, 3, 4.
Soldier 7, where are you? We need your help.
Yeah.
And then 1, 4. Okay.
Oh,
So
We started one time. Just for Ray, go ahead. What do you want to take out?
if it was 1, 2, and then
Here.
3, 3, 4, 3, 4,
My
and
house.
then any digits in common.
I'm sorry, you know, I haven't noticed there's like a little intergalactic battle going on. The fate of the universe was, you know, lying in the balance. What was your example?
If I have 1, 2,
Yeah.
2, 3, 3, 4.
Yeah.
The 3, 4 doesn't have any digits in common with the 1, 2, but they're still part of the same rule.
It'll still match the 4x4 rule. And it'll still work. It just needs, I need 4 squares that are only 4 numbers or n. Right? That's what's happening right down here when we say, hey, we have n squares that all contain n notes or fewer. And the logic still works. We know that those 4 squares, if they have 4 numbers among them, those 4 numbers must be in those 4 squares. That's what's going on. Anything left over, if the answer is yes, then we can remove those leftover numbers from all the other squares in the target block. So essentially subtraction. So we're going to say B1, and then I'll just come over here and I'll say, hey, B1 is the target block, and B2 is the source.
Okay.
Block. That may not be the greatest terms to use, but I'm just, you know, we could also just say the first block. We could, instead of target, might be easier than the first block that we subtracted from. That's probably easier to think about, like that.
Yeah.
I'll just write this instead of first block we subtract from.
I think this is a good time to stop.
I think you're right. What we also have to do, let me just finish the notes here. Set subtraction the other way. We have to check B1, B2 minus B1. Here's the first slide. Okay?
Okay.
Anything left over? Yes, so we can remove those leftover numbers from all the other squares. That's important. All the other squares in the first block that we subtracted from. That is the killer thing right there. Now the problem is though this. See this line of code right here, Campbell? Or this comment that says, yes, we can remove those leftover numbers?
Yeah.
See that? Well, the problem is we don't have that first block at this point. We have to somehow get that block or do it later, right? Because all we're getting is a group of 9. It's a column or a row. We don't know what block it's associated with. We need to do a little bit more. We need to have a deeper understanding of the board, of where we are, and somehow the ability to either modify the board now or go out, add to a list of commands that we execute later after we're done with the solving in this process. So in other words, in this process, if we can infer things about other cells, other squares that are not in this group, which is what we're doing in this logic, we need to somehow add those to a list of, hey, things we're going to do later. So for example, we might have a command, you know, a later commands, you know, something that looks like later commands dot add, and then we're going to say a new remove command, and that's going to take a parameter that's going to be maybe my block, like B2 or whatever, and then it's going to be my list of numbers that I can remove, like maybe just the number 3, like that.
Okay.
Or maybe a 1 and a 3. You know, but 4x4 rule could potentially remove 2 from the others. So we're going to do something like that.
Yeah.
Okay? All right, let me get it ready to go. Kayla, thanks so much. I thought you did a great job. Loved, by the way, today, right? Just want to reemphasize. You saw a problem and fixed the problem, right? All by yourself. First time you've done that, you should feel pretty proud of yourself. All right, we're going to send you over to White Panther. Here we go.
Okay. Goodbye.
Bye.
See you
Good
tomorrow.
luck. We'll see you tomorrow.